Is that the moon right over your head, Lulu? That's cool
Yeah.
outside. That's a cool. Are you outside? Yeah, that's
Yeah.
cool. I feel like I might as well
It's
be
really
outside.
cool
It's so
here.
cold in my living room.
I know, but the air's like so fresh and crisp that you know, I don't want to sit inside.
I like the cloud. I like the clouds too. You can see yeah, that's cool.
I thought it was a green screen. I'm like, that's a wicked cool effect, man. It looks so real.
No, she just lives someplace.
Israel.
You just live someplace awesome. Because the Seattle
Israel.
area is still wet and yucky.
It's probably like 40 degrees here. You know,
It
in
was
Houston,
7 degrees today. It was -2 degrees up in the mountain in here in Mass.
Well, whose
But it's
fault
just
is
sunny all
that,
day.
Jeremy?
No,
I
just
figured
Dave's
like
fault.
alignment, you know, perfect alignment, then I could capture space time at the same moment everywhere. Like, you know, if I could do that exact 90 degrees.
Like this whole thing, pretty much. This is
What do you guys think about the new that telescope, the Webb telescope that launched? Don't you think that's really cool? Like, you know, what all the cool stuff like it's been gathering. I watched today a video about how it's gathering the light in, you know, into like the center to create one picture. But I didn't know that a lot of these stars that we see could be replicas of just light bending. You know, so that was really interesting today. Anybody has any input on that?
I haven't been following the James Webb Telescope, but my understanding is, I mean, they have that multi-mirror array. They just finished unfolding that, if I remember right.
And I find it fascinating how that mirror array is in a honeycomb shape. It's like a half a buckyball for its geometry.
It's like little, they're lifting like the light, they're bouncing the light from like one platform to like one mirror to the other, to the other, to the other, like into the center to create one picture, you know, it's really cool. And I mean, the orbit on that thing is wacky, but it's really cool. Like at one point it becomes before Earth, so it picks up data that is incoming. And then at one point it goes, you know, behind Earth. So it picks up the, you know, how much data transferred through Earth. It has the coolest orbital if you like look how it's going. You know, it circles the Earth, but at the same time does like a loop.
Do you mean
really
half
cool.
the time it's like facing the Earth, and then it's like as it goes, that it's facing outer space sort of thing? So it's like 50-50.
Yeah, that whole like, you know, loop, like, you know, as the globe is rotating, the thing is just going like this, and you know, like forward and then backward. It's beyond, you know, awesome. So, and at the same time, it's orbiting the sun. So, I mean, it created like a new moon, but with an opposite orbit, like literally. You know, still, you know, the physics behind it is, I think, is really awesome. Like, just wow.
Any other questions or anything here?
I posted in the chat the link to that NASA article about the lattice geometry of the cold fusion. If Lucian,
The Hackaday one, right?
Sorry,
it's not the Hackaday link. Let me just see. I gotta see where you posted that. It's in the live chat, you said?
yeah, of the Zoom.
Oh. Let's check this out. Lattice confinement fusion. They're very careful not to use cold fusion, the words. So Peter Hagelstein did a number of presentations on this. He's got a really interesting theory on these super strings, like coherent matter waves, and he thinks that there's deeper physics going on inside these lattice structures, which are and this is MIT, who's been working on it for a number of years. Really interesting stuff with the here's a video on it, right?
I find it fascinating when mixed with Walter Russell's diagrams. Not necessarily a fan of Walter Russell per se, of his metaphysical stuff, but the geometry and scaling and universal scaling, mixing the geometrics with the mathematics is pretty intense, and it connects in with the Platonic solids and those shapes and whatnot. But basically, it's the lattices of the covalent bonds form into different Platonic solid geometries depending on where in the octave scale it is, and then the crystals of those lattices form in those same Platonic geometries. Sorry to take everything right off left field there.
It looks like the screened OP process will help mitigate the loss in efficiency from the lattice, because you have this lattice of these relatively larger atoms absorbing some of the neutrons that are flying around, like in a traditional fusion reaction. So you probably have a lower efficiency because of the lattice, but some of that is recovered because the erbium can actually donate, I think it was neutrons and I think both, right? Neutrons and protons to the reaction. But then over time, those will be saturated. So I think that's what that's what needs more development. I wonder if you could use cryo-deuterium in a crystalline lattice itself. In other words, like just heavy hydrogen ice. It has to be very cold, but we're trying to do this in the vacuum of space for space propulsion. On the subject of non-traditional fusion, a long time ago, there was this notion of what they called sonoluminescent fusion in water. Did this go the way of some of the other so-called cold fusion schemes that they say are, I guess, in very dubious scientific status at best? Or is there something to some of that? You guys remember some experiments when there would be
sonofusion never went anywhere.
Oh, that's too bad. That was an elegant idea.
Yeah, it was a nice idea.
Cavitation, though, right? It was a form of cavitation.
Yeah, yes, it was. It wasn't sonoluminescent, it was sonofusion. That was what it was. Yeah, Bernie, you're right. It was a form of cavitation. The idea was when the bubbles collapse, they collapse at a speed that's fast enough that they thought that it might actually create some kind of a fusion pressure. And so it was, yeah, it was one of these oddballs. I think they did some tests on it and it just didn't go anywhere, and then it fell out of favor, you know?
More of a plasma reaction than a fusion reaction.
Was there even any fusion at all? So there it was just maybe plasma, like you're saying. Just there
I don't
was
know.
Never...
I mean, the entire idea was premised on this, you know, the
shrimp, right?
Well, the entire idea was premised on that the bubbles collapse so fast. That was the idea, right? These bubbles
Oh,
that
the
are in
star and the
it,
star part.
they collapse at like a speed that's faster than, you know, the speed of something, and therefore, you know.
Was that shrimp the idea of Thanos in the Marvel comics?
Yeah, what type of shrimp was it again? The
Pistol shrimp.
Sorry?
I think it's called a pistol shrimp.
Pistol shrimp. Yes, that's correct.
That's a cool video. We should watch the pistol shrimp. Let's watch this one with Sabina. Let's see what.
Quick question before we change the subject, though. Is the pistol shrimp's cavitation the same as the star in the jar experiment that they did in the lab? Because I don't know if the pistol shrimp puts off light from its cavitational reaction or if it was just extreme heat. Is it the same or is it different? Another major part of it is in regards to the geometry and the octave scale in charts that Walter Russell did, and I believe that they are essentially the same knowledge as Plato's Platonic solids and Pythagoras's harmony of the spheres in octave scale, and that they understood these geometries, and that basically, have you guys ever seen Walter Russell's vortex-based periodic table?
I just saw that on a Google image search. I haven't been able to investigate it in any detail, but amazingly, it resembles a mathematical construct called a sieve of Eratosthenes that gives us the prime numbers and has a mathematical structure of the Riemann Zeta function, a powerful mathematical tool that is the center of a Millennium Prize investigation.
I definitely need to look up everything you just mentioned because I am not familiar with
What this Odic periodic table?
the bottom left there. Right below the Odic periodic. The Walter Russell one there. Far left, good sir.
Interesting arrangement, you know. Just going up in the electron shells.
The main part is that each half circle is an octave of going back and forth, and along that octave are the Platonic solids, and that each element will then crystallize in that shape of the corresponding Platonic solid that it is in, and that by knowing those geometries and crystal formations, you're able to calculate the resonant frequency or the harmonics of it a lot easier, and then use the same corresponding metals on higher or lower in the chain of the same geometry to be able to transmute it much easier. Another major part or thesis of this cold fusion or natural electrolysis cold fusion, plasma cold fusion, is that it's a very, very minute amount of energy required, and it's more of just like a single bump vibration of the molecule in and out when it's changing its nuclear state or its mass, as opposed to the hot fusion where we're literally required to fill space, which is like the paradox of how empty the physical space is in a molecule, in everything, where you have, for hot fusion, you're literally having to fill all of that space with pressure, with heat and energy and density to the max, at where it's like literally the ultimate everything you'd ever, the most amount of energy you could ever require, as opposed to this cold fusion vibration or natural resonance that is like the least amount you could possibly be required, sort of thing, like a single little photon, or yeah. Does that make sense?
That's a lot like action principles. When we talk about deriving a physical law from first principles, we go to an action principle like Hamilton's principle of least action, or before that, there were earlier versions, or I think now it would be due to any other slightly more advanced form. But what it basically says is that natural processes do the extremum of action, of work, or sometimes I forget what it is.
Essentially the inverted opposite.
They're either
five.
the most work, the most action, or the least, right? And this seems to have tremendous just philosophical implications. So many times the people that contribute the most in the arts or the sciences oftentimes get the least reward for it. Mozart dying in poverty, things like this. Edgar Allan Poe never getting his due in his lifetime. It's interesting. So, for instance, general relativity was never derived from first principles by Einstein, but the mathematician David Hilbert did derive general relativity from an action principle. I don't know if entropic gravity is a very interesting approach. I've never seen it done from first principles. People think that theory just came out in the last 10 years, but actually a guy, Ted Templeton, I think, derived it in about 1994 just from Hawking's area entropy relation on black holes. He was able to derive the Einstein field equation.
Hey, John. So I already did some work on a gravito-electromagnetic acceleration, and we found out there's an offset with the theory in the experiment. So I'm just a heads up that the theory is just done by analogy. It's not derived, or it's not by observation. So that's why it's completely, there's a huge offset with the theory and the experiment. So we did some work on that already, and we're not the only ones. And also, I'm just theorizing that time is energy, is a form of energy. It's not a dimension. So just a heads up here. But basically, I just want to say that the theory of gravito-electromagnetism is completely wrong. So just a heads up.
Do you believe that gravity is entirely solenoidal then? So there's no curl, what do you call it? There's no curl to any gravitational field. There's not a B field, or that it's extremely tiny if there is a gravitational magnetic analog. So right in electromagnetism, we have the two fields, electricity and magnetism. And typical alignment, you'll have the kind of Coulomb type solenoidal field that's attractive, right? Opposite charges attracting.
Yeah.
Then you have the structure of the magnetic field, and this is stable. And this would seem to kind of counteract gravity. But in the case of gravity, of gravito-electromagnetism, and gravito-electromagnetism, it's deemed to be extremely small. And you're right there. I don't think it's derived from first principles, and like you say, I don't think there's a universally agreed upon magnitude of this force because it lacks a clear derivation.
Yeah.
But and experimental results are all over the place.
Yeah.
So I think there was a satellite finding that was published maybe about 2 years ago that suggested that the magnitude that was theoretically calculated was 10,000 times too small. Now, this is still very small. People are still searching for an engineering application if it were 10,000 times larger than it even was deemed to probably be. But what I'm hearing, in your opinion, you think that there is no gravitational B field, or it's extraordinarily small.
Well, there's one, but it's much more stronger than what the theory says, because the theory is not derived. It's just done by analogy with the Maxwell equations. So they just compare G with K, which K is the inverse of 4 pi and epsilon 0. So there's a huge lack of amplitude there. You can't just copy and paste these variables. So I'm trying to figure it out.
You think it is? I think I heard though that you think that the magnitude of this B field is actually larger than originally predicted. I'm in agreement there. There's a good publication out last year, and this is from the flawed theory. It has no experimental basis, but the mathematics is sound. And these guys say that dark matter, as we've known it, is in trouble. It's a Springer publication. They're very well respected. They say that if gravitomagnetism, I leave out the electro because we're talking about the B field. If that B field does have a larger magnitude, we won't need as much dark matter to explain cosmic motions that are observed.
Yeah, I think I saw part of that article that was wanting to explain, replace the dark matter. I have another explanation for dark matter, but I'm not gonna get into that. Yeah, it's just a heads up here. Just don't rely on what's written in wiki pages on the gravitomagnetism.
The jury's still out on that one. Thank you.
Yeah. I'm doing some. I'm trying to learn quantum physics now to derive it correctly this time. That's what I'm doing.
There's this apparent schism between classical and quantum mechanics. However, there's an approach to quantum mechanics that deems classical mechanics to be the limit of quantum mechanics as we take perturbations of the Planck constant and take it to a vanishing quantity. And then we recover classical mechanics.
Yeah.
And this is kind of a justification of ideas like the Bohr atom before we understood that the electron did not have a precise location. And on an earlier theme that Bernard was talking about, where alchemy and these early theories have some validity, I believe that the old geocentric hypothesis actually has some value in this light of the connection, the inherent connection between both types of mechanics. Because what happens is in the geocentric theory, we had the notion of deferent and epicycle. These amount to the first two terms of a Fourier series expansion of the position of the planets from a Cartesian coordinate perspective that is centered on the Earth. But then everyone would say, oh, but the Earth is not the center. And I would say, no, the ancients were sophisticated to choose the Earth as the center, because we know in relativity that there is no center, there is no preferred location. So what the best thing to do is to use your location as your coordinate center. Those are called FLRW coordinates, Friedman, Lemaitre, Robertson, Walker coordinates. And so the ancients were actually using a central tenet of applied relativity when they calculated upon the geocentric hypothesis, and the Arabs came later and formalized this with a early form of Fourier series. Now here's the kicker. You're putting a solar system in terms of a Fourier series expansion, and Fourier series, you say you're learning quantum mechanics. Fourier series and Fourier transforms are the quintessential tool for quantum mechanics. So in the theory of or the theory of quantum electrodynamics, you use the space of functions that have Fourier transforms and inverse Fourier transforms, called the L2 function space. So the geocentric hypothesis with solar systems as Fourier series actually deforms to a quantum theory in a different way than just taking a limit of the Planck, taking an inverse limit of the Planck scale going away from zero. You also can transform the variable in the Fourier series from a integer or natural number, like you have integer valued frequency modes. You can transform this into or apply this to real precision complex numbers. And this basically amounts to taking the Fourier series instead of along the integers on the real number line and taking it continuously in vertical strips in the complex plane. And what this does, it transforms that series in with another coordinate transformation from integers to logs of real numbers. This takes that series into a different kind of series called a Dirichlet series. And it's related to a different kind of integral transform, just like the Fourier series related to the Fourier transform. The Dirichlet series, which represents quantum states, is related to an integral transform called the Mellin transform. The beauty here is that this takes information processing algorithms and makes them into algebraic equations, much like the Fourier transform takes differential equations and makes them into algebraic equations. So we have a union in, and you can express this, all of these models on one smooth manifold using information geometry. And it's basically that the rational points or the integer points on that manifold are the classical theories, and in between are the quantum theories. And these Dirichlet series combine like quantum states. When you multiply them, they form an algebra, and when you multiply them, there's a very simple isomorphism to the tensor product. When you have a basis, it would be called the Kronecker product. It preserves all of the structures of quantum states of complex systems, which that state space is called a Fock space. And there's a lot of beautiful stuff with Fock space, and its ultimate limit, say its metric closure, is a beautiful space called the Bergman-Siegel space, an analytic space of functions of incredible complexity that's been used to prove stuff like all kinds of new results in quantum and complex analysis, which apply back to conformal field theory. If you go look at the classical side of all this, if you merely perturb all of these kind of circle-based Fourier sums, if you take perturbations of them, you get these shapes called hypotrochoids. If you ever played with Etch-a-Sketch toy as a kid, you ever have that one where you can put these like cogs on paper with these plastic ones with pins, and you rotate them around with a pencil inside, it makes these cool little loop-de-loops. But there's a really sophisticated mathematical structure to this space of spirographs. That's right, I forget what I was trying to say, but this space of these shapes called hypotrochoids contains the central algebra of superstring theory called a Virasoro algebra. So we literally see this intense relationship between the quantum and classical theories. And it's just striking that basically the ancients were on the cusp of quantum gravity. And maybe these folks that believe that folks, in ancient times disappeared, there's these various theories that certain civilizations, were able to teleport off into space or something. If there's anything to that, they would have had to have the technologies that would be implied by an understanding at some of these levels.
Sorry, Mr. Quinn, I just wanted to ask to clarify, you were saying that these ancients were able to merge quantum and classic theory, is what you said?
I will back up and just say that they were perhaps at that cusp, because at the very least, their mathematical tool of the geocentric hypothesis, the mathematical tool brought by the Arabs, and they may have got it from before, was the theory of epicycles, right? So when we look at the theory of the geocentric hypothesis, and it's a textbook bad theory, your teacher probably told you in school, see, the ancients were wrong because they drew one circle for the orbit of every planet, and they said, oh, that doesn't work. So then they drew another little circle to make it work. Right? You ever see that one where they draw Homer Simpson with all these little circles rolling around? That's because you can use a Fourier series to draw any shape in the plane. And the ancients were on the cusp of discovering the Fourier series that allowed us to have a mathematically rigorous theory of heat. Right, that was the first thing Joseph Fourier, I forget which Fourier, there's a couple of them. That's the first thing Fourier did with it, was to solve an equation called the heat equation, a partial differential equation that's not solvable without doing all of this. And it also allows its close relative, the Schrodinger wave equation, to be solved. So if they didn't get that far, at least they were at that apex. And it's a simple change of coordinates to a different route to quantum mechanics. And that's new work. I'm trying to publish that part where we go to the Dirichlet series that's closely related to fractal geometry, prime numbers, and the Riemann hypothesis. The Riemann zeta function is a Dirichlet series.
Thank you, sir. I appreciate that. I just wanted to say very quickly to everybody here, I am not a scientist, physicist. I'm just trying to learn. So please forgive me if any of my questions seem a little bit overly simplified or vague, but thank you guys. Thank you.
There is no bad question.
Yes, thanks for asking that question. I'm sorry for all of these any mistake. I'm sure I made many of them. They're all due to me. But everything that I've said correct is due to people that taught me or people that I've studied.
Well, along that line of thinking, if I'm not taking up any other people wanting to ask questions, I was quite amazed when you guys were looking. I just hopped in when you guys were looking at Walter Russell, if I'm not mistaken, his depictions from, I believe it was the Universal one. And although I don't understand the science behind it, although I'm trying to self-teach in a way, you had mentioned, sir, Mr. Quinn, about the implications philosophically relative to the wave picture that we were looking at about maybe 20 minutes ago. You were saying it's either one extreme
You know
or
what?
the other.
You know what? Let me just try to share an image that reflects the similarities between the Riemann Zeta function and the periodic table. So the philosophy, I probably am forgetting where I was at right then, but I want to try to find this image because this object that I invoked, the sieve of Eratosthenes, it's usually not shown in this form. And it's very hard to pin down this kind of imagery. There's a few different representations of this mathematical object. It's basically as simple as writing out all the numbers, and then you skip every other number and cross them out. Why? Because they're all multiples of 2, so you know they're not prime. Then you skip every third number and you cross them out, except for the first one of each of these classes. You cross out every third number after 3, because they're all multiples of 3. Got to get them out of here. They're not going to be prime. And you just keep doing that. You can, if you're smart about it, you don't have to do stuff like 4 because you already did 2 and stuff like that. But it's a no-brainer. If you don't want to be smart about it, you don't have to. But that just makes kind of a blocky image. Usually folks do it, they go 1 through 10, 11 through 20, and so on. And so it kind of destroys the part where it looks just like Russell's periodic table in some of his images. So I wanna upload that one. But there's a different interesting case. There's actually a few different ones, but there's a different case of the sieve of Eratosthenes. It's also very interesting using lines. And this one to me almost looks like kind of the Nazca lines of Peru, or the almost like pyramids or something. But I'm getting into pure speculation, or my fascination with watching those documentaries about the ancients and stuff like that. There might probably be nothing to some of that stuff.
Are you aware of prime quadruplets and that mathematical series and the energy with them in relation to Coral Castle and Ed Leeds-Gallen's work on electric magnetism and magnetic current?
Sounds like twin primes, but just even rarer.
Prime quadruplets, 4 prime numbers together, or sets of prime numbers. It's very advanced mathematics that I haven't refreshed myself on in several years, so I'll have to share that next time. What you were talking about, did it have to do with magic squares at all, or the vortex-based mathematics too? Or it sounded more like it was along the lines of Nassim Haramein's holographic universe and Schwarzschild proton theory, I think it's called.
I know that Nassim Haramein is a string theorist, and some of these ideas are adjacent to parts of string theory. String theory, in my view, is a mixed success. I don't want to call it a failed research program, but it's a mixed success. But it gave birth to what I believe is its more successful progenitor, entropic gravity or emergent gravity. And that theory has its problems. Someone mentioned the philosophy of it, and some people say emergent gravity has a fatal flaw at that kind of ontological level, that it puts entropy as a fundamental concern, when entropy is a kind of side effect of the arrangement of things.
Yeah, I'm not really a fan of the string theory either, and it wasn't along that aspect. It more had to do with that all complex information is contained in the shell of the orbital or of the circumference of the atom, or the just geometry of whatever it is, the energy that has that is carrying through the time, I guess. It's how holographs are able, just through one little slit of a 1D, to be able to recreate all the information, the complexity in the full 3D when you put the light through it or whatnot. Does that make...
I actually agree with a lot of that, but I think string theory didn't go far enough. So there's brane theory, but as a fractal, so basically now we have strings, so called, but maybe it's 2-dimensional. Maybe you have a 3-dimensional brane, and what about its modes of vibration? And it gets much more, difficult to calculate, especially when you start talking about 4, 5, and even 10 and 11 branes, right? However, there's also dimensional surfaces, let's call them, of real valued dimensions. As a fractal person, we can't forget that maybe you have the dimensionality of the Cantor set, and this object can also vibrate at frequencies and give rise to soliton formations, basically. I just posted a link. It looks terrible. I'm sorry, I didn't know it was so horrible. But this is one of the rare images that is much like Walter Russell's periodic table, but this one is just an abstracted image. And what it's showing is this process of striking out the composite numbers in the sieve of Eratosthenes. The other version I was talking about that kind of looks like a perspective, it looks like a treatise on perspective geometry. And what's so amazing, and I think this is going to be key to solving the Riemann hypothesis, if you draw lines of every monic fraction slope, but using pixels, just pixelated dot-like lines on a grid. So it's similar to striking out every other number. You're going to make a 1/2 slope kind of line of dots. Then you make a 1/3 slope and a 1/4 starting from that integer. Actual parabolas form, curved curves, conic sections that are squares, right? Like, basically graphs of x squared translated by something. There's another connection between the parabola and the sieve of Eratosthenes called the Matiseyevich sieve. I probably didn't pronounce that right, but this one gives us a statement about, it just basically is a common sense statement of prime numbers not being composite, but it puts it in visual form and lends it to analytic exploration when you think about what's called the tangent bundle. There's an isomorphism of what's called the tangent bundle. So the space of all the tangents on a parabola is isomorphic to the space of what you call the secants, where you cut the parabola in 2 points. That's where the composite numbers come in. So every kind of point on that parabola that intersects at 2 integers can't be a prime number, more or less. I'm saying it wrong because it's not in front of me right now, but the Matiseyevich sieve. But hopefully that link at least works. I'm sorry it's like this giant, like 3-page link just for a relatively low quality image. But
it's like a side or cross section of a conch shell essentially, but the sine cosine waves keep going and going, and then starting from the beginning connecting with each one.
I think so. Yes. their sine and cosine waves, or their let's just call them trigonometric functions, or right, but they're kind of like on logarithmic coordinates because they're stretching out.
Sorry, I just had a quick question with respects to entropy. The only way that I was even able to think of the concept of it, or for it to come to my mind, was watching the film Tenet by Christopher Nolan. Is there anything in theoretical science? Is there anything that would be able to substantiate that, even theoretically per se, that with respects to the entropy of an object?
I haven't seen Tenet. Can you explain a little bit?
Yeah, so very briefly, essentially what happened is that the protagonist, the main character, is briefed on what's happening, and there's basically humans from the future sending objects back in time. And what happens is that a scientist is showing the protagonist the way in which the object is able to be picked up by feeling it. So essentially, she puts a bullet on the table and says to the protagonist, catch the bullet. And he goes, what do you mean catch it? She goes, you have to, this is when it gets a little bit like, I guess you could say rabbit hole-ish, but she goes, you have to have dropped it in order to catch it. So she said, it's not so much about trying to understand it as much as it is about feeling it. But then he then did that, and the bullet went into his hand. But when she played it back on the camera, he was dropping the bullet. With respect, do you see does that make sense? It's all about perception, depending how you look at it. Was he dropping the bullet, or was he catching the bullet, so to speak, if that makes sense? No matter which way you play the tape, back or forward, it's still the same concept, but it's a matter of, I'm sorry if I'm not explaining this correctly, but it has to do with essentially entropy inversion, if I'm not mistaken.
That's very deep. So we're all familiar with this second law of thermodynamics, and we're kind of beaten over the head by it and given a wrong impression. So there's this idea that, because first of all, one thing I want to say is I feel a great deal of acceptance here. I'm really grateful to come here and meet everyone and share ideas. And I think that this kind of thing needs to spread out through society. We need to, whatever our views are, a gentleman, an invited speaker was expressing some views about our current pandemic situation that I might not agree with, but I respect him and I want to hear more, right? So I just want to say that let's use these ideas to help everyone that we can. And in that regard, we have this concept of entropy, that the world is running down. This is false. Okay, at least at a large level. I understand there's problems like pollution and so on, but the world is far from equilibrium. So keep that in the back of your head, because we're going to talk about just regular old entropy where thank you, where everything does run down. So what happens is there's this concept called entropy. When you have now I don't know how to answer that scenario. That's a fascinating scenario. Time travel hasn't been ruled out in physics yet. I consider myself working to rule it out, and I'm fascinated by it. And I'm fascinated by fiction where it does happen, especially when they make the effort to make it consistent. Okay. Now that's another aside that I'm going to leave aside, because let's just explain the basics of entropy. Sure. So if I have a system where things have probabilities of happening, that's called a probability space, to abuse the language, right? And I can calculate a measure of like disorder in such a space. It's just a simple calculation on that space. And as I evolve such a space, this quantity called entropy does not decrease in a full probability space. So probability space, there's 100% probability that all the different things that can happen, one of those things will happen, right? So that's 100% of the probability. If you leave any of that out, if you leave any of that probability out, now in the part of the probability space you're looking at, this whole thing of entropy must always at least not decrease. Basically, it must always increase. That goes out the window because all that entropy could be shoved in that extra space. Okay, and this is what people are missing when we have this idea that there is no free lunch in this world. Okay, if there was no free lunch in this world, how is it everyone lives longer, better lives? I'm able to talk to, I don't even know what state you're in, and we're talking about entropy through, and we could see each other and stuff. There is improvement to be had in the world, and it's demonstrable, okay? This is because we're in a far from equilibrium situation. We haven't closed the system. We don't even know if the universe is a closed system. And this gets back to the idea of trying to disprove something like time travel that appears to conflict with the second law of thermodynamics. But it's even conceivable that there could be reverse time travel, because obviously forward time travel happens all the time. We're time traveling into the future at 1 second per second. And relativity theory tells us, just plain old relativity theory tells us we can kind of speed that up. The closer that you go to the speed of light, moving clocks run slow. So you're basically time traveling into the future. The big question on time travel is, can you time travel into the past? And it might even be possible to do that in a closed system in full agreement with the second law of thermodynamics. And I defer to anyone that knows better. That might be a false statement. I'm sorry if I'm making a mistake. But there is a project to show that no, you can only go forward in time, because that's what seems more sensible. However, at the quantum level, we know that all of that goes out the window. The arrow of time is more of a probabilistic thing where most stuff is going into the future, but there's a small proportion of particles that are antiparticles. And it can be demonstrated that antiparticles are equivalent to regular particles traveling backwards in time. This was actually a statement of Richard Feynman, if I'm not mistaken. So if you look at Feynman diagrams of an electron, of what's called electron-positron annihilation. So you have an electron and a positron, and they're cruising through space, and they meet and they release energy. But this could also be an electron that completes a loop in space-time that is initiated, the reverse part of that, by an impact with a gamma ray, the same gamma ray that's released when the electron and positron meet. Now this is the stark difference between quantum scale physics and the physics of our lives. So once you get to a macroscopic scale, you're talking about basically Avogadro number levels of numbers of quanta. You're talking about 10 to the high power of particles, and now these things that are fairly uncommon at the quantum scale are virtually unknown. Although some of us might be aware about quantum teleportation experiments, I think they quantum teleported now, correct me if I'm wrong, something like an amino acid or maybe a whole virus or something. People are talking about quantum entangling entire microscopic animals. Quantum entanglement being a related issue that has many similar paradoxical properties, where there's some information exchanged, it's not usable information, but it's exchanged without any time elapsing. So that's almost as bad as reverse time travel. On another sense, some folks don't view quantum entanglement as, like, some people make a bigger deal out of it than others. So the quantum entanglement is not a big deal view can be summarized by saying, if there's a black marble and a white marble, and you shuffle them in a bag, and you pick one out of the bag without looking, and you walk away from that bag, and you walk 1,000 light years away from that bag, and now you look at the marble that was in your pocket and it's black. So you instantly know, without waiting for the speed of light, which would have taken you a year to look at the bag and see that there's a white marble inside it, you instantly know there's a white marble in that bag. However, quantum entanglement, as envisioned by Einstein in his 1935 paper with Podolsky and Rosen, was intended as a thought experiment to crush the validity of quantum mechanics. And just in 2013, it was discovered that he had a follow-up paper in 1937 where he related this entanglement to wormholes. So there is a school, it's called, that hypothesis. So the original hypothesis in 1935 is called EPR. This is the birth of quantum entanglement. Quantum entanglement is a big part of the new approaches to gravity. There's basically a whole family of new approaches to gravity that kind of sprung from, in some sense, the decaying corpse of superstring theory. And not that it's not an active area of research, but many of us were unsatisfied with it. Then the new theory that started getting attention in 2013 is called ER equals EPR. So if you may have heard of Einstein-Rosen bridges, the wormholes, the scientific name of that is an Einstein-Rosen bridge. And Einstein's paper in 1937 with Nathan Rosen hypothesized that entanglement was the same as the space-time geometry of wormholes. And many of us are using that as a starting point, hand in hand to some extent with understandings about entropy and its mathematics. Not as much, I mean, at that level, we're not looking so much at the philosophy of entropy, but the mathematics of it. It has beautiful formulas involving the logarithm, because these states, there's so many states that you have to like just look at the power. Basically, you had to like get rid of the number and just look at the power. So instead of saying like 1,000,000, we'd rather look at like 6, right?
Okay.
And so like entropy uses that kind of mathematics, and that kind of mathematics is closely related to fractal dimension. And it's the view of my research group, my other research group. I feel at home here and feel like I hope to make contributions here, that this is going to be key in contributing to physics. My PhD advisor has a 900-page book on the Feynman integral. So he's a physicist when he's not at being a mathematician. Someone posted, entropy seems to be winning in our universe. It's really hard to uncook a steak. That's a philosophical view. I mean, my thesis here, what I really want to get out there though is like, no, dude, new children are being born. They're individuals that like you couldn't even envision, you know, like some great artist is being born probably right today. You know what I mean? And we could never imagine what beautiful vistas they could create. Like Rob Chambers says, it's easy to raise another cow. Perfect. Yeah. Even though it's hard to uncook a steak. Maybe you eat the steak, you poop on the ground, you fertilize it, a cow comes, eats that grass. I mean, these processes rely on the fact that the earth isn't a closed system. And there's a lot of beauty to this.
You should connect to the WhatsApp group, APEC groups. You know WhatsApp?
We have the legendary John Hutchinson himself in the YouTube live chat. Would we be willing and able to post a link for him to join the Zoom if he's so willing and choosing to. And much respect, great sir. We love your work here.
Well, anyway, thanks, John. It's very interesting, but keep in mind that time can be an energy, not a dimension, which you could dilate it, contract it, but you wouldn't be allowed to go back in time. So that's my
What
theory.
What about polarity, positive, negative? That leaves a permanent indicator in space and time. That's how, you know, we know if we left energy or we did not leave energy in that spot of space that the planet has moved in. So polarity would be a form of, you know, trying to find out to go back into the past. You know? I mean, it's going to leave a positive or a negative. So looking back at it, it could be a start to a whole derooting what happened in that time segment, like embedment of a code basically in the universe on the most primary element or residual that it could leave, you know, evidence of, you know, something was here. And it builds, you know, back from that all the way to, in that time segment of time, you know, what the universe was like.
You could have something there. Bernard mentioned that John Hutchison might be able to attend. I'd love to hear from him. This Hutchison effect seems to defy entropy. You know, with entropy as this concept that basically grows with time or doesn't decrease with time. Some folks have the notion of time. Philippe was talking about an alternative notion of time. Some folks have the notion of time that it simply is kind of the inverse function inverse of entropy. And I'd love to hear from John. He's such an enigmatic person from what I've seen on, I've only learned about him through this community. I'm not up on the Hutchison effect, but if I could call you Lulu, this is very interesting. Yeah. If there could be bidirectional time is what I glean from the notion of time as having a polarity. I don't think that's entirely ruled out just yet, but I think that it's considered an extreme claim. And a burden, when we make an extreme claim, the burden of proof is on us. So at the everyday level of reality.
I'm getting this like idea or vision from, you know, like radiation, leftover radiation. Well, leftover radiation, that's like a, you know, a stamp of polarity in time, and, you know, gradually like dissipates, but it means it leaves a mark in time. And same thing, you know, with polarity. Polarity is either going to be an element that moves on to become something else, like what earlier the videos we were watching, or it's going to decay and just wither away, and it's not going to have any potential energy. And so that's how we know, you know, whether it was a positive effect or a negative effect in time.
You know, someone told me that the indigenous people of Australia believe that, unlike in the West, where we believe we're facing the future and the past is behind us, they think you guys are so stupid because you can't see into the future. So we're facing the past in their philosophy. This is how it was explained to me. I'm sorry if anyone knows better. This stuff.
Well, wouldn't it depend on the solar system spiral arm and the direction it's going? Then we know if we're going to the past or the future.
Like I'm just speaking in just crude terms about like birthdays and life and memories, right? Like I can remember the past, so I have that kind of vision, and I can't remember the future. So I can't metaphorically, I can't see the future. So for them, the way it was told to me, they view us as facing, you know, and viewing backwards. So for them, this notion of time travel, I guess would be congruent with memory. And the forgetting then, you know, is congruent then with entropy. And it seems like you could build a kind of serviceable notion of physics around a perspective like that. I don't know if ultimately it would lead to any novel interpretations or new physics, but philosophically, it is a big difference. I am committed to this view of I'm looking forward into the future, but ironically, I can't see it. I mean, I can attempt to predict it. But if I could, is John Hutchison in here? I'd love. And the other thing is, there's a guy, John Hutchinson, who's huge in my field. He's probably my favorite in fractal geometry, because his theory of fractal geometry is the simplest. And part of my ambition was to put everything in terms of John Hutchinson's theory. If folks have done fractal geometry, there's a simple way of making fractals called an iterated function system. And John Hutchinson put that all together. He's a professor of mathematics at Australia National University. I think his key publications were in the early 80s, but I saw a presentation of him from quite recently. He still looks relatively young, and I was quite amazed. John Hutchison, from what I'm seeing, seems very interesting, kind of like a rock and roll kind of personality, right? I don't want to offend anybody or say anything, but he seems like a really interesting person. And he's so I think one of the key observations was like a levitating bowling ball. And I postulated diamagnetism as the first explanation I would reach for, because you had a Van de Graaff generator, you had you just had all this high powered electrical stuff. And I said, well, you know, yes, these aren't electromagnets per se, but they are going to generate an electric field. It's going to have a associated magnetic field. And that's the only thing I got in this situation. How in the heck is a bowling ball gonna levitate? If you've seen experiments with strong neodymium magnets, if you take like something that can float, a little Tupperware little dish, right? And you put like a block of wood in it and put that in a tub of water, right? You have a block of wood in a plastic boat, and you take this super strong neodymium magnet. You have to approach it relatively close. I mean, within millimeters. But these magnets, I think they develop about 15 Gauss, and it will actually repel this wooden block due to the phenomenon called diamagnetism. A lot of you guys are really great at physics. I'm not so much, but what I think is going on there is that the magnetic field is so strong that the electrons in the molecules of virtually every substance will align with that magnetic field and hence be repelled, or align against it, I guess is what it would be, and hence be repelled. Diamagnetism is a way that magnetic fields can repel virtually all non-ferro or paramagnetic substances, depending, of course, on their density, for the magnitude of the repulsion. And to me, this reeks of unifying electricity directly with gravity. I'm only just recently kind of thinking about this in some detail. I'm pretty sure in this group there's some people that that are up on the details of why it's not that simple. But at the end of the day, such a just in your face connection. I just can't imagine it not panning out. And the way that I'm envisioning it is through this geometry called information geometry. I was attempting to explain that quantum theories and classical theories can all inhabit the same kind of higher dimensional space. The interesting part about information geometry, so classical information geometry is more restricted to the space of statistical models. The key ones being those that model normal distributions. So it's stuff that's connected with a normal distribution. Data sets that are well described, well fit to normal distributions, all fit on a two-dimensional flat manifold. And this manifold has a lot of geometric character. It has a metric tensor, and it has something called a divergence, which is even more detailed than a metric tensor. Divergence is like distance. If any of you guys skateboard or snowboard or ski, and it's like longer to go one direction than the other in terms of physical effort. It's the same distance by a measuring tape, but for some reason it always takes longer to go up the hill than to come back down. And that kind of way of measuring distance is, strictly speaking, that's a mathematically sound object called a divergence. And if you want to ever recover a distance from a divergence, you just add the difference. You just add the distance in both ways and divide by 2. The space of
All right,
these
isn't that the gradient is the slope, and the divergence would be like how much the curvature of the hill, like how much it spreads out.
I was confused by that word divergence. It's a different use of the word. You're right. Divergence is kind of the spread. Yeah.
Right.
So in this gets back to electrical theory. So typically in an E&M setup, the roles can switch, but typically the electric field is the solenoidal field that has divergence. That's the one that's spreading. And the magnetic field is the one that has curl, and it's the one that's conserving its volume. You see that toroidal field around the Earth, but then the charged particles that are shooting out of the poles, they shoot out into space. That's the electric field shooting out there, and the toroidal field is the one, I forget what you call it when you have curl. It's not solid. Solenoidal is the one that has divergence. Another word is divergence free. And then when you have divergence free, that's the word I'm looking for, but there's a better word for it. It's the vorticity, vorticial, something like that. That's a field that has curl, but that's a different word, divergence. In computer science, there's this word overloading. So we have these like terms in computer programming or computer science that mean multiple different things. Divergence is an overloaded term. It has this other meaning. So let me just call it, instead of divergence, I'll call it Bregman divergence. That's one example of a distance metric you can put on what's called a statistical manifold, and that will reduce confusion with analytic divergence, which is so you have that del operator, the nabla, right? The triangle guy, the upside down triangle. And
Yep.
So del dot a vector field is the divergence. Whereas del applied to a function of however many variables, whatever dimension you're in, gives you the gradient. So there, right?
Partial differentials. So you take a partial differential for each dimension, and then you add them together, and that will give you the divergence.
Yep. Yes, because it's dot. Yeah, that's funny. But del applied to that function of three variables takes it from one variable, so to speak, f of x, y, and z, to, you know, the three components, the three partials. But then del dot, the three partials, takes you back to, you know, the real number line, just one value.
Yeah, the trace of the Jacobian matrix, right? Of an n-dimensional vector field of n-dimensional spaces invariant under invertible linear transformations.
I would probably be a little rusty on that, but I will say then the curl is del cross the vector field. So the cross product. And then there's a better way, there's a few different improvements on this, because the cross product only works in 3 dimensions. And so you need either an exterior algebra or a Clifford algebra to apply this. If you want to find vorticity in, say, Einstein space-time, which is 4-dimensional, you're SOL. You can either leave out time, but then you're not working in space-time, or do some other nonsense. And that other nonsense, you'll probably end up stumbling on the exterior algebra, the exterior product in the exterior algebra. But probably a more consistent way is a Clifford algebra. So I was talking, but what I wanted to say about information manifolds was that that whole side with trying to study Dirichlet series. There's one form of Dirichlet series I'm always obsessed with. It's called the Moran equation. So there were 2 gentlemen in here named Moran. I kept trying to ask one of them if he's related to PAP Moran, that found this equation that's kind of like this, what I would call a scaling equation for fractal geometry. And this these equations, even though they have many coefficients and exponents, they're asymptotics. The way they behave, kind of when you boil them down, you know, when you do crank all the machines and get the answer out at the end, basically, this fits on a 2-dimensional information manifold. I don't know if the same can be said for Fourier series, but based on the idea that I'm trying to say, that Fourier series is basically a Dirichlet series under a change of coordinates, then it would be true. And this is something that we have in conventional physics right now, this conformal field theory, which there's an idea in there called a ADS CFT correspondence, where we can get quantum gravity in 3 space dimensions by doing regular quantum physics on two space dimensions. Someone posted something, spaz.org, Magi, thank you for the compliment. I appreciate that. Let's see, wave articulation matrix. Interestingly though, the word Magi makes me think of magic. And I probably spent an hour I didn't have this morning or last night typing a Facebook chat to a young friend of mine, and about what would happen if the universe were truly infinite. And we can't rule that out. If the universe were truly infinite, would there be a notion of a closed system, for one thing, in the conversation we've been having? But if you, I guess I won't get into it because it took me an hour just to type it down, but there's this book called The Whole Shebang by a science writer, Timothy Ferris. And he has this long discussion of the philosophical ramifications of Descartes' demon hypothesis. How do we know that we're really here versus maybe we're being tormented by a demon that gives us hallucinations? And in the modern school of psychology, this is maybe our brain is in a jar somewhere being stimulated by electrodes and made to perceive what we deem to be the world around us right now. But it's not about that kind of matrix level of like simulationism. It's not about that. The discussion he gets into, what he gets into is the improbability of certain quantum states, like a conscious mind perceiving what you're perceiving right now. People think they can calculate the probability of that happening, whether it's really you or me, or whether it's even a system that spontaneously forms. Now, that's extremely unlikely, but remember, physicists can calculate, for example, the probability that every gas molecule in your room will suddenly go to just one corner of the room, leaving you to suffocate until, you know, the gas molecules will eventually return and fill the room. In all likelihood, if you're lucky, if you're reasonably lucky, which is, you know, 99.99999% and beyond, it will do that. But, you know, there is some chance that all the gas molecules, for that matter, could stay in the corner of your room. You would literally not have a chance to breathe unless you found the right corner. Anyway, and I guess the pressure there would be really high. But so armed with that kind of knowledge of probability spaces and quantum states, and the geometry of space-time where quantum states occur, there's a certain distance at which you could expect for certain situations to happen. So if someone believes that they could cast a magic spell, let's say, and they try and it doesn't happen, let's say, I mean, it's just going to be most people that have belief in magic and they use it in their life, it's kind of more metaphorical or internal to their mind state. But I'm talking about people that have telekinesis or can make a fireball or even a nuclear explosion just with their mind. That the odds of something like that in a truly infinite universe, there could be somebody that is just like the person in our world that thinks they can do this, that does it, and they think that they actually caused it just with their mind, even though it's merely just a fluctuation of probability. And I went into an extended discussion of that. I don't know if I explained that very well, but there's a better discussion of it in Timothy Ferris's book, The Whole Shebang. So I was trying to look at this link, wave articulation matrix. This one, oh, that shape looks like some of these objects. This is very interesting. You know, this full loop antenna, these lengths look like they are in the proportion, like they're like 1/n type lengths. They're distributed like what you call the Gabriel's horn, you know, the 1/r, the graph of 1/x, right? But then just taking the integer values. So 1, 1/2, 1/3, out to infinity. And an antenna of this shape might have the desirable characteristics of a fractal antenna. So a lot of us are aware that antennas have disappeared from cell phones. Some of us might be too young to remember antennas on our cell phones, but I actually worked on cell phones back in that era, and they came out with this little metal tab that they put usually near the battery of the cell phone to get rid of needing an antenna. And you say, wait, but that little tab isn't even an integer multiple of the wavelength. We used to have the antenna, and it would be a very precise shape because we needed an integer number of waves to fit on that antenna. Now we just use this kind of randomly shaped little tab. Why is that? That's because it has a self-similar geometry and it's in a higher dimension than 1. So it has an infinite length, basically, for all intents and purposes. And it can pick up a wide assortment of waves, or even in principle, it could pick up all waves because of its fractal dimension being greater than 1, again, giving it basically infinite length for a practical purpose. Just to describe right now, this object having these this relationship 1, 1/2, 1/3, if that's what that is, if that's what your antenna is not typically deemed a fractal. However, hear me out. There are several different notions of fractal dimension, and fractal dimension is what's usually used as the line of demarcation from classical geometry to fractal geometry. And the simplest notion of fractal dimension is called box counting dimension. And many people reject box counting dimension because it allows this set 1, 1/2, 1/3, 1/4 to be considered a fractal. I consider it that's actually a strength of that fractal dimension, but that's a whole other issue. It gets back into the Riemann hypothesis. I don't want to talk about that anymore, but interestingly, I will conjecture that this object should be able to pick up a broad band of frequencies, even those that are too long to fit on in any kind of sensible way on that antenna. Has that been your experience with that? And I hope it is, because this would lend credence to this notion that the box counting dimension has nothing wrong with it. Yes, Gabriel's horn, awesome. And you found the golden ratio in it. I wasn't even aware about that one. Bernard, thank you so much for pointing out the work of Walter Russell, is it? Of Russell?
Yes,
that's amazing stuff.
And thank you for everything you have just shared too. I'm gonna have to rewatch this like 5 times just to digest it all. But that is the beauty of this APEC and the intellectual discussions that are now here and possible. It is a very beautiful thing.
I have to defer to APEC. I'm learning more than I'm saying. That's for sure. I'm so grateful to everybody here. It's like I said, the biggest thing is, dude, we got a welcoming space. We're all here in good faith, trying to freaking serve our fellow humans, and in fact, whoever else, right? All sentient life. I feel like that's our goal. It's like in Star Trek, like a Federation of Planets type stuff. And
exactly.
Yeah.
I often ponder the idea, are we not allowed off of this plane until we stop harming ourselves first? And once we make peace with our own species or planet and life forms, that then we will be able to join the galactic community.
Yeah, right now we are rejected from the galactic community. Maybe there are aliens within us, who knows?
Absolutely. John, there's a lot of requests in the YouTube chat that you be booked on for a future full-length presentation yourself, because you are putting forward just a tremendous amount of higher dimensional mathematics and information and thought process in general, and it's amazing. You're well loved in the community so far.
Thank you so much. I will be honored. I just got a new job, and I've been going through, and many of us, I don't mean to draw attention to myself on this. Many people right now are struggling in many ways. There's a global pandemic afoot. There's a associated financial hardship, and so my schedule up until now has been fairly unpredictable. I tend to have Saturdays free though, thank goodness. My other research groups are during the week, and I'm sadly not able to attend them as much as I would like. So moving forward, I would say I probably cannot accept the honor of a full presentation because my work right now is in education. It takes a great deal of my time to prepare lessons. Working with our children, our children are our greatest treasure, and all the time in the world isn't enough to devote to bettering their circumstances. But I really look forward to partaking in further extended discussions, and as I get my life situation further straightened out, I would be honored and very happy to accept the honor of presenting in a full format, because I feel like gravity was my motivation going into studying mathematics. I said, let me study mathematics as a shortcut to learning physics. And then my PhD advisor, like I said, he wrote a book on the Feynman integral. So he was a physicist in a sense, but he's a mathematician. Michel Lapidus, the great Moroccan, French, American mathematician at UC Riverside. Someone mentioned Jack Sarfati. That's Jack Sarfati, the founder of quantum cryptography. That's his alma mater as well. And what I found was that mathematics has a proliferation of tools, perhaps an embarrassment of riches, to offer to physics. So much of the difficulty in physics resides in the problem of resolving singularities. And there are entire schools of mathematics that are just full of ways to treat the singularities. Let's, just as an example, if you consider the Big Bang singularity, there is no way, even just in physics, that comes to a point. So if you've been skeptical about the Big Bang coming down to a point, I would tell you, well, even in orthodox physics, we have uncertainty. So how do we know which point it would come down to? We have a theory in mathematical physics, but it's well known in physics, called Leoville's theorem. So there's a smallest amount of what's called phase space, kind of a space of speeds and locations, and you're not going to get smaller than that. So between those two things, the notion of zooming all the way back down to the original point that everything came from, that's false. And even Stephen Hawking, who's a fairly orthodox general relativist, he even abandoned the hope for the initial point of creation and described a Planck scale object called a P instanton. So most folks understand this, but fractal geometry offers the hope of putting a little more structure on that initial singularity. In my view, this is when you start getting into my research, not well accepted. I haven't done a postdoc. You guys, let me just confess right here. I haven't done a postdoc. I have few publications. I have one peer-reviewed publication and my doctoral thesis. So, this is when I try to let you guys know when it's my work versus if I'm trying to be a conduit of other information, and my mistakes are my own mistakes. But I think that the perspective of geometry in real number dimensions, which comes to us from fractal geometry, and indeed my advisor generalized this to complex dimensions, which is a fairly complicated notion to explain in detail, but it is in overview exactly what it sounds like: dimension with an imaginary portion as well. And this feeds us information about what's called the oscillations of self-similar objects. So as you, I don't want to get into it because we haven't gotten into just how is dimension defined. But those of you that know some about fractal dimension, you can probably imagine now a little bit more generalizing from the real numbers to even complex numbers as working for dimension. So yeah, I understand there's another APEC on the, is it the 30th already? Or that, I guess that wouldn't be a Saturday.
14.
Yeah, that probably won't be one in another 2 weeks. So that will be the 30th, I believe, the 29th. The 29th. Yeah, I'm about to wrap up this live stream here online. So if we can, much love
Thank
for
you so
everyone
much.
who joined
so
and
much.
out there in the comments. Thank you guys so much. We can continue the discussion here on Zoom, but it won't be broadcast and there won't be the live stream. So this was a fascinating discussion. John, thank you, John Quinn, for joining us and sharing that fascinating perspective with us. Lots of
Mr.
cool stuff
Quinn,
to look up now.
Sorry, before you end it, Jeremy, John, if you could post your email in the private chats or send me a direct message, it would be appreciated. And even if not a presentation, that maybe just get you on a talk with me and Jeremy sometime of just a random discussion when you do have time, good sir.
It's wonderful meeting everyone. Thank you so much. Stay safe.
Thank you, John.
Thank you.
Thanks.
Thank you everyone watching and have a good night, and we'll see you guys again soon. Later.
Take it easy, guys.
All right, so that stream is ended and we can continue with the party.
Very cool stuff.
Tim, are you still with us, or he might be AFK? I'll tell him he can end the recording on the on his end as well if he's ready.
Tim might have fallen asleep an hour or two ago.
It happens, man.
What an amazing lineup though, and group of people and discussions today though. That was awesome.
Yeah, I was looking up a ton of stuff during that open discussion. I just keep going on Wikipedia from article to article to article to article. Like, oh, look at all this cool stuff people can look up and learn about and research, like academic level stuff. That's great. I hope we introduce.
You know, the other day I was reading something about like the elementary particles and their decay. There's a possible like of 103 to maybe 150 different fields of these particles that could be in existence. So, I mean, there's so much that we don't even know yet. You know, we only know just like the smallest layer of that. And it could go
Right.
like
That's what happens in these particle accelerators. That they know like the proton energy that they're creating. They know the energy levels that they're creating when they smash these. They collide these two hadrons, these two protons together in these accelerator experiments. But what they get out of the mix is like different every time. It's completely like random, and they'll get like different things with the energy. The amount of energy they have could be transformed so many different ways by the quantum vacuum to produce all kinds of different things.
Yeah, very interesting.
Hey, on the particle decay, they found out that prior to sunspots forming, the decay of particles on the Earth actually change, and because of that, carbon dating could be totally wrong.
Oh yeah.
I read a couple of papers on it. It's really interesting that they found that, although it hasn't been reported like you would think they would be screaming about it, but they haven't. But a lot of people have been saying carbon decay, using that as a way to measure time has been wrong for years, but now they kind of got papers that show that something's going on with the sun changes the way things decay on the Earth. So it is
I wonder
wrong.
if there's any like scientific court cases that have ever been settled based on that science that they'd have to overturn if something like that were.
Probably would have to, but it's really interesting that that's the case. So what it's saying, it tells me, is that there's something going on with the energy field that the Earth is in around the sun, that the sunspots change that energy field for just a limited time prior to the sunspot actually pushing out materials and stuff. There's an energy change going on in the vacuum, is what it says.